Hi, we are from Group 9. Now we would like to present our electrical machine assignment. Our presentation outline will consist of introduction, test 1 DC test, test 2 block rotor test, test 3 no load test, and the last test is about the torque speed characteristic. After that, we will have a short conclusion.
Hi, Assalamualaikum. Today, we'll be discussing three-phase induction motors, which are commonly used in industries due to their simple construction, strong durability, and high efficiency. To better understand how these motors perform, we carry out four key tests: the DC test, the block rotor test, the no-load test, and the torque speed characteristic test. For consistency, we use a preset value of 9 throughout the process. These tests help us extract important parameters and gain deeper insight into the motor's behavior under different conditions. Okay, this is test 1. The first test we conduct was the DC test, which is designed to determine the stator resistance, denoted as R1 of the induction motor. This is a fundamental parameter in the equivalent circuit model as it directly affects the stator open copper losses during motor operation. In this test, a DC voltage of 5 volts was applied across two terminals of the stator windings. Since the DC has no frequency component, the inductive reactance of the windings becomes zero, and the only opposition to current flow is the pure resistance of the stator coil. We measured the resulting current as 2.725 amps, and using the basic formula, which is R equal to V over I, we calculated the stator resistance to be 0.2725 ohms. This value of R1 is later used in both the copper loss calculation and to isolate the rotor resistance during the block rotor test. The DC test is important because it gives us a precise and straightforward way to obtain a parameter that significantly influences the performance and efficiency of the motor. Thank you.
Hi, my name is Wong Chuen Yu, battery number A230063. Now I will continue with the test 2, block rotor test. This is a test which simulates a condition where the rotor is physically prevented from the rotating. This situation is show the short circuit test in transformers. By looking the rotor and applying a small three-phase voltage to the stator, we force the current to flow through the stator and then into the rotor circuit without any mechanical rotation. We vary the applied voltage from 1 volt to 5 volts in measuring the corresponding phase current and input power in each case. And from this value, we will calculate the total impedance, power factor, equivalent resistance, and also the equivalent reactance. And this table is the result of the test 2. By using the stator resistance obtained in the test 1, we isolate the rotor resistance R2, and by assuming S1 equal to X2, then we are able to calculate each component of the leakage reactance. The average power factor across the all voltage levels was around 0.17, which is expected in the block condition due to the dominance of inductive effects. The leakage reactance X1 and X2 were found to be approximately 2.135 ohms for the each. The results was consistent except for the small dip at the 3 volt, which could be due to the nonlinear behavior in the simulation or the transient fluctuations. Additionally, we are calculate the stator and the rotor copper losses, which it can help assess the motor's internal energy dissipation during the start-up or heavy load condition. In overall, these test tools have given us the critical insights into the series component of the equivalent circuit. And next, we will continue with the test 3, no-load test, which is similar in principle to the open circuit test of a transformer. Here, we allow the motor to run at the nearly full speed with no mechanical load attached, and apply a red phase voltage of 217.4 volts. And the motor reached close to the synchronous speed, meaning that the slip was nearly to the zero, and as a result, this very little current was induced in the rotor. This condition has simplifies the equivalent circuit and effectively isolate the magnetizing branch of consisting of RC, which is core loss resistance, and the XM, magnetizing reactance. And then by refer to our calculation, we have measured a phase current of 3.1 per ampere and the input power of 117.3 watt. By using these values and after subtracting the stator copper losses calculated from the R1, we have determined the rotational losses, which has included the core, friction, and the wind tail losses. Most importantly, by using the phase voltage and current, we have calculated the magnetizing reactance XM to be approximately 67.37 ohms. This large value indicates that the motor's magnetic circuit is efficient and does not draw excessive magnetizing current, which is desirable for the efficient steady-state operation. So this test was crucial to complete the shunt component analysis of the equivalent circuit. And that's all for me. Thank you. Now I'll pass to my next member.
Hello everyone, my name is Wu Minghua and matrix number is C230061, and I will present about the test 4, which is the simulating top speed characteristic of three-phase induction motor. And as we can see, this is the circuit of the test 4. So now we will set up the value first at the asynchronous machine. So we will set to 9. So the horsepower will be 10 and the voltage will be 575 watt. Frequency will be 60 Hz and the rotor speed will be 1760 RPM. So at the input, we also will set the 575 voltage based on our preset parameter. So because I already run the circuit, so we just go through for the result of the graph to find out our maximum value of to find out the value of maximum torque and the rotor speed. All right, as we can see, this is our result graph for our test flow. So now we zoom in the graph first. All right, around here. And so now how we find out the maximum torque and the rotor speed in this graph. So we are using the theta cursor and we just move the cursor. So we just move the cursor at the maximum peak of this graph. So as we can see, we need to focus for this blue one. This is our torque value. So we just adjust the value to find out the maximum torque of this graph. So as we can see, the maximum torque is 163.9 and the rotor speed will around 1530. So let's see our calculation part. So for this test flow, we need to calculate the N sign, which is using the formula 120 times frequency Fe over post, and we will find out our N sign is 1800 RPM. And next will be our maximum torque value that we just find in our graph, which is 163.9, and we're using this value to find our maximum S, which we're using the rotor speed in the graph, which is 1530.1 over 1800, and we will get the S max 0.85. So the last we will find out the efficiency value. So we're using the output power divided by the input power times 100. So finally, we will get out the result is efficiency is 26.94%. So for the conclusion, for this project, which is the electrical machine, are important tools that help power modern life. So they play a big role in many areas like industry, business, and everyday life. So this machine help increase the automation, support cleaner energy, and improve industries such as car, manufacturing, and energy. And they also help the environment by cutting down emission, using less energy, and promoting eco-friendly practice. And that's all the presentation from me. Thank you.